All right, well, did you figure it out? Let's think about this. Let's say that we've gotten to a specific point, and let's indicate that as such. The algorithm that computes by rows will do so partially by rows until it gets to the diagonal, and then go by columns. Let's just assume that the matrix is stored by columns in column major order. Computing by columns is good, computing by rows is bad. So this is not an ideal algorithm, because part of the computation is going to be by rows, and of course as you go farther and farther into the matrix, and as the matrix gets larger, you'll end up with more of the computation happening by rows. And if you think about it a little bit, roughly half of your computation will be by rows, roughly half will be by columns. What about the other algorithm? Well, the other algorithm will go by columns, but notice that it has the same problem. The elements above the diagonal are not stored, so you look towards the row instead, and therefore you go by rows first and then by columns. Same problem. It also does roughly half of the computation by rows and roughly half of the computation by columns. So I actually would expect these two algorithms to perform roughly the same, because roughly how they bring data in from memory is the same, and when you don't reuse data, that's where your expense is going to be. All right, well, there are ways around this. One possibility is to say, well, when you compute by rows, inherently you're bringing in cache lines. We talked about that a little bit last week. So can't we just kind of work 4 rows at a time, which then would mean also working 4 columns at a time? And can't we then do better? And that's indeed how people would go and optimize this kind of problem. And that is actually, and that then motivates what we're going to see are blocked algorithms. Okay. Now, about 10 years ago, we doodled a little bit on the blackboard using the notation that we now use in the course. And we actually came up with a better algorithm. It's an algorithm that only goes by columns. And it just happened to be that the person who at the time provided the world with the fastest open source linear algebra libraries was in the room. Someone named Kazushige Goto, a colleague of ours. And when we derived the algorithm and described it, he overnight implemented this in his library and improved the performance of symmetric matrix vector multiply by a factor 2. So what did we learn from that? The algorithm was not obvious to an expert and gave considerable performance improvement to a community that cares very much about performance. So what I want you to do is to kind of stare at this and kind of scratch your head and kind of think and see whether by just looking at this algorithm or this program as implemented with indices, whether you can puzzle it out. And then in Unit 2, we're going to systematically derive algorithms for symmetric matrix vector multiply. And you're going to find out that the answer drops right in your lap. Enjoy this week.